My name is Eli Asarian with Riverbend Sciences, and I'm on the KBMP steering committee. And I'm going to introduce, or I'm going to be the MC or whatnot for this late morning session. So thank you all for coming back. And thanks to Randy and Mike for facilitating the morning. So our first speaker today is Laurel Genzoli, and she is going to be presenting her research on the effects of the McKinney Fire on ecosystem metabolism. So Laurel, you can share your screen and get rolling. I will be quiet.
Awesome. Eli, are you seeing the presentation?
Yes, all looks great and I can hear you fine. So please go ahead.
Awesome.
Thank you.
Well, thank you. Like Eli said, I'm going to share some analyses that I've been working on with the Kuru tribe on the post-fire effects of the McKinney Fire debris flow. And so I'm going to try to move myself off the screen a little bit here. Okay. Whoops, let me see if I can, there we go. This is a project I've been working on with Grant Johnson, John R., and Bob Hall. And like I said, this project is being led by the Kuru Tribe DNR. I love this little series of photos here showing all of these awesome folks doing good river science in the lab, in the field, and on the whiteboard. And I think most of you on this call should be pretty familiar with the McKinney Fire, but if not, just a little bit of background information for you here. The McKinney Fire burned in late July, or it started in late July of 2022. It was a super high intensity, really fast moving fire. It burned a couple hundred square kilometers along about 25 river kilometers of the Klamath River. And most of that area was burned super rapidly. It caused pretty massive destruction around the community of Klamath River. And you can see in these plots that Jenny Curtis made, much of that area was burned at really high severity. And then on the evening of August 2nd, there were super intense monsoonal rains that dropped upwards of 4 inches in about 3 hours on top of the actively burning wildfire. And those rains caused these super severe debris flows, primarily out of Humbug, Vesa, and Little Humbug creeks. And a huge amount of sediment was transferred to the river during those intense rains. And again, Jenny Curtis led a project that looked at exactly how the fire and rains kind of interacted to manifest these debris flows, and also the immediate impacts of water quality as it was registered at the tribal monitoring sites along the river. And so what this showed was that there was a modest increase in flow, but it transferred a huge amount of turbidity, which then caused this big dissolved oxygen sag at Seiad Valley, and much more minor, but still noticeable dissolved oxygen sags downriver at Orleans and Klamath at Turwer. And so this project showed us kind of these immediate impacts on water quality, but it was pretty limited to those immediate impacts. And so Grant sought out some funding and was able to put a project together where we're able to focus on what these long-term effects are. And when I say long-term, I'm going from essentially when the fire started and those debris flows were initiated through December 2023, because looking beyond that would be just severely muddied by the dam removal and the sediments coming in from there. So we're kind of looking at this midterm scenario after the fire. And why focus on ecosystem processes? This wasn't part of the initial analysis of the short-term impacts, but I'm going to back up here for just a minute and share with you all kind of why we're focusing on these ecosystem processes in this project. From a water quality perspective, we often focus more on turbidity and dissolved oxygen, which are things we can measure with the sondes. And we know that turbidity has an impact on dissolved oxygen, but that effect is not a direct effect. And so there's a few different ways that turbidity impacts dissolved oxygen. It can have an impact on ecosystem respiration, where you get more carbon and other elements washing into the water, and those are being respired in the river, and that can cause decreases in dissolved oxygen. But turbidity can also and does also have a huge impact on the amount of light that the river is getting, especially in rivers like the Klamath, where the production is coming from algae attached to the bottom. And so turbidity reduces light, it reduces gross primary productivity, and then that has an impact on metabolism. And so this is just showing kind of some of these more complex pathways in which turbidity can impact dissolved oxygen. And so I also just want to point out, for those folks that might be less familiar with what ecosystem metabolism really is it's referring to both the gross primary productivity, which is all the photosynthesis that's occurring within a reach of stream, and it's also referring to respiration, which is all the consumption of carbon and the transfer of carbon in the river. And so those two components are what I'm going to be talking a lot about today. And together, they're really the biological processes that determine dissolved oxygen levels in the river. You'll also see air-water gas exchange on here, because this is the third component of what's driving dissolved oxygen levels, but it's a physical component, and it tends to stay relatively stable with or not relatively stable, but it changes with discharge rather than with biological changes to the river. And like Maya, I'm not going to go into any of the modeling that we use to do this work, but I will just say that these fluxes of productivity and respiration that I'm going to be talking about, we're able to model from the daily change in dissolved oxygen. And that data is data that in this project was collected by the Karuk tribe. And it plays into what Randy was talking about in his introduction about how important and full of information these long-term data sets can be for addressing some challenging questions for the Klamath River and rivers more broadly. So we sought out to learn some things from the McKinney Fire. We wanted to look at how long the impacts of the McKinney Fire lasted beyond that immediate and really obvious effect it had on water quality. We also wanted to look at how much ecosystem metabolism and water quality changed after the fire. So again, after that initial really big impact from the turbidity, kind of what were the magnitudes of change? And then to what extent did these subsequent pulses of high turbidity, how did they affect the river? Were there, or to what extent were there additional kind of more dramatic effects on metabolism and dissolved oxygen after the fire? And when I started this project, I kind of had this idea that, like, okay, cool, we're looking at this data and we're thinking about what can we learn about fire on the Klamath River for kind of future understanding and management of the Klamath River. But when I started reading about fire's effects on water quality and metabolism, I started to really see that there's a pretty big knowledge gap here. There are overall very few studies that show the impacts of fire and turbidity pulses on dissolved oxygen. And there's even fewer studies that look at the response of ecosystem metabolism. So how fires are impacting the productivity and the respiration in the river. And what I found was there's this dominant idea that the impacts of fire actually should increase production because a lot of these studies or for the few studies that are out there, many of them are looking at how fires might burn riparian areas and actually allow more light to the stream bed, how they can increase nutrients and fuel productivity in that way. And so we kind of had a counteracting hypothesis to some of the dominant literature on this. And then finally, I'll just point out that no studies that we were able to find show the effects of wildfire on stream metabolism in a way that they're comparing the baseline, how the river existed before, what happened during the event, as well as after. And so we have an opportunity here not only to learn about the Klamath, but to contribute more broadly to understanding rivers and wildfire through this research. And this is super important because burn, stream, and river miles are increasing in the Western United States. And we can see that from the study here. And the amount of river miles that are being affected are not just river that's in an active fire, but we know from this work on the Klamath and other studies that the rivers are often affected far downstream from the burned area. And again, like Randy was saying, this work is really only possible because of this long-term tribal monitoring. And from this monitoring, we're able then to expand on what we know about the Klamath, but also it's helpful to rivers beyond the Klamath as well. Okay, so in this project, we focused on presenting data from Seiad Valley, which was the closest continuously operating sonde to the debris flow. And you can see on this map here, the McKinney Fire in orange kind of in the center. And then these are the three main debris flow watersheds. And Seiad Valley here is the monitoring station that the work was done at. So this was a decent way below the debris flow. And so we can imagine that anything I'm presenting here would likely have kind of more extreme impacts upstream and then attenuating downstream. Okay, so this is just quickly, again, looking at the immediate impacts of the fire and that initial debris flow where we had a little increase in flow after this intense rainfall that happened on the active wildfire. And then we had these large turbidity peaks coming, likely coming out of these three main watersheds, and dissolved oxygen plummeted in step with those turbidity peaks. But it did not last very long. The impact was extreme. It caused a big fish kill. It caused anoxia, but it didn't last very long. And so we wanted to then step back and look at, okay, what's happening now in the 17 months post-fire? And we found that turbidity increased significantly following the fire. It went from an average of 3.9 NTU in the 4 years before the fire to 18.2 NTU in the 17 months after the fire. And turbidity stayed high throughout that whole time period. There wasn't an obvious decrease that happened up until the time of dam removal. Also, the relationship between turbidity and flow really eroded after the fire. So before the fire, high turbidity really only occurred at high flows, and you can see that in that purple line on purple dots on the plot. But after the fire, high turbidity occurred both at high and low flows, and that relationship between turbidity and flow, or kind of seasonal turbidity, really fell apart. And that the increase in turbidity drove a really dramatic decrease in metabolism. So productivity went from an average of 8.7 milligrams of oxygen per meter squared per day down to 3. And respiration also, which is represented as a negative number, it also decreased. The flux went from 6.9 to 3.6. So you can see strong seasonality prior to the fire. And you can also see a lot of kind of reflection of respiration in that productivity. But both respiration and productivity really suppressed after the fire. This plot here is just showing the extent that respiration and productivity reflected each other. Before the fire, most days on the Klamath River were autotrophic, which are dots below the black line. And what that means is that most of the biological activity in the river is happening associated with algae and plant growth. And so this kind of in-river production prior to the fire transition to where there was more external inputs driving biological activity after the fire. And you can see that with more dots above the black line. So we moved from a mostly autotrophic to more heterotrophic river after the wildfire. And you can see that with net ecosystem production, which is the balance of production and respiration, shifting from 1.7 to negative 0.4 from before to after the fire. Despite, though, this more negative production to respiration ratio, daily minimum dissolved oxygen was actually higher generally after the fire than before the fire. And I'll show a few exceptions here in a minute, but overall, we see that this lower production, which caused lower respiration, led to these lower daily swings in dissolved oxygen. And those big swings is really what's responsible for these low levels of dissolved oxygen that occur in the summertime on the Klamath River. And kind of counterintuitively, that ratio of production to respiration was less important than the magnitude of production and respiration in relating to these minimum dissolved oxygen levels. And I did want to just quickly share this plot looking at what happened after the fire, kind of in an event-specific way. Number one here is that initial sediment pulse, and you can see up in the top left how that drove dissolved oxygen really low. But we had 7 other events where turbidity was over a median of 50 NTU per day after the fire. This never occurred in the data frame or the data set prior to the fire. So we had all of these events with high turbidity, and in general, turbidity did suppress productivity immediately when it was happening. It really shut down the amount of photosynthesis that could happen in the river. But a lot of these even relatively high turbidity spikes did not have a high respiration signal along with it. Only in the summertime during the initial event and the resuspension event in August 2023 did we see a big dip that actually went below the water quality threshold. So what we're finding is the river was pretty robust overall to these moderate levels of turbidity and even relatively high levels. So just to summarize here, the extreme turbidity event that caused anoxia and a fish kill was a really, really extreme water quality event for the Klamath River, but it was pretty short-lived, and the persistent moderate increases in turbidity that followed were really, they lasted for the duration of the study, and they caused more than a 50% reduction in productivity and respiration in the year and a half after the fire. And that lower metabolism ended up causing actually fewer days of low minimum dissolved oxygen than before the fire. So kind of some unexpected results, I guess, when we're thinking about how extreme that initial event was compared to kind of the moderate and potentially some positive impacts following the fire. And again, I just want to point out the extent that this data set contributes broadly to wildfire and understanding wildfires and river ecosystem response more broadly, and how important these long-term data sets are. One thing that this paper or this project really contributes is that, there's this dominant, like I mentioned earlier, this dominant expectation in the literature that fire actually might increase production. But here we showed that when the fire impact is high turbidity, it is more likely to suppress metabolism, especially in the midterm post-fire. One thing we weren't able to answer is how long these impacts last, because the study, period ran up to dam removal, and we can't tease that out. And so it would be really interesting in the future to try to understand how long these turbidity events could last if we have another big turbidity event or another big fire in the future. And while extreme sediment pulses can cause anoxia, these moderate increases in sediment were able to decrease some of the DO violations. And I'm going to kind of point out that this could be positive in a eutrophic river like the Klamath, where productivity is higher than ultimately it probably should be. But we don't really know yet how much turbidity is needed to curb the effects of high GPP, and it'd be really interesting to put some numbers on that and try to understand how restored sediment regimes from dam removal potentially might also help impact and curb GPP a little bit, and if that would give us positive impacts for dissolved oxygen. And then I'll just end by saying with increasing climate and fire uncertainty, again, this long-term continuous monitoring is a great example of a really informative impact of being able to do this kind of monitoring and research and contributing where others haven't been able to provide this information due to lack of monitoring. And with that, I am happy to take any questions or take any in the chat if we're out of time.
Thanks, Laurel. We do have a good amount of time for questions. You finished perfectly at your time slot. So, but we have this little 5-minute or less buffer. So, Allison.
Hi, Laurel. Excellent job to you and your team. So I think you said that you guys didn't look beyond those 17 months, but can you just generally say how the post-McKinney fire conditions, like the turbidity, diel, and stuff like that, compare to reservoir drawdown and dam removal, like during the 2024 year, just a general characterization?
Yeah, I mean, we did cut this project off due to just having a really hard time interpreting results after dam removal and disentangling those two impacts. But I think one thing in terms of impacts to ecosystem process is that the really high fluxes of sediment and really high levels of turbidity with dam removal were in the winter, and productivity is already low in the winter in the Klamath. And so that relative impact of going from like 2 or 4 grams of oxygen per meter squared per day down to 0 is pretty small relative to when the McKinney fire hit and we'd be at 20 milligrams of oxygen per meter squared per day down to 0. And so being able to like plan an event like dam removal definitely can help lessen the impact on the river than these events that are not predictable and not, at all controllable. But like most folks on this call probably know, the Coffer Dam breach that had to happen in the summer would likely have a similar effect to what that initial McKinney pulse or the resuspension event that happened because productivity was higher then. So there was just more to fall.
All right, thank you.
We have time for another question or two. If anyone has any, I thought there was 2 hands right away, but then one of them went down, I think. So any other questions for Laurel? Maya.
Thanks, Laurel. Sorry, I was trying to turn on my video, but I can't. That was great. I wonder, in terms of the other, like, what is your assessment of the other impacts to ecosystem functioning given the decrease in primary productivity? Like, I know that wasn't the focus of the study, but I'm just curious what you think in terms of nutrient cycling or just how the Klamath River behaves in a kind of, normal year. So it's this kind of question of like, what does it matter?
Yeah. I mean, I think one thing that's interesting with productivity is we often talk about limiting nutrients, but you can limit productivity through nutrients or through light. And the Klamath has so many nutrients in these upper reaches that they're probably often not very limited by nutrients. And so here we had light becoming this like limiting factor for growth. And so there probably are a ton of nutrients that came in with this, but adding more nutrients if you don't have light isn't going to increase productivity. Mm-hmm. And so I think in the downriver reaches, you might end up getting this shift where you have less turbidity, and the nutrients then, if they were limiting to some extent, might be able to increase productivity. There could be a bit of a shift, but yeah, we would have to do a whole lot more analyses to like get into the extent that that's true and how far downriver that effect might happen.